video, we're going to talk about what a basis is for a vector space. So just a reminder, a vector space is a set of objects, which we will call vectors, but you, again, don't have to think of arrows like you draw in physics class. And there are two operations, addition and multiplication by scalars, defined on the objects. And for it to be a vector space, those operations have to satisfy the following 10 rules. And so we went over those in the previous video about vector spaces, but importantly, the set needs to be closed under addition, meaning if you add two of the objects, the new sum is in the set also, as it is defined. And it has to be closed under scalar multiplication, meaning if you multiply an object by what you're considering a scalar, that new result has to be in the set as you defined it. And you need a zero. You need something considered a zero such that when you add it to an object, it does not change the value of the object. And then there's the other rules, commutative addition, the order that you add doesn't matter. Associative addition, you can group objects and add them and then add a third, and how you group doesn't matter. Various distributive properties, and there needs to be a scalar that's equal to 1, and there needs to be an opposite of an object such when you add two opposites you get the 0. So that's a little reminder about vector spaces, and we're going to talk about what a basis for a vector space is. So the basis of a vector space is a minimally spanning set. Okay, what do we mean by a minimally spanning set? It means that it's a set of vectors that spans the full vector space, and no fewer vectors are needed to span the vector space. For example, any three independent vectors in R3 form a basis for R3. So here 1, 2, 3, 6, -5, 3, and 8, 1, 13, those are independent vectors and they form a basis for R3. Also, the simple standard vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, they also form a basis for R3. A reminder to tell whether or not vectors are independent is to RREF your column vectors, and if you get the identity matrix, then it means that those vectors are independent. Or if you RREF the vectors that form the pivot columns, those are the independent vectors. So the three vectors we had, 1, 2, 3, 6, -5, 3, 8, 1, 13, when you RREF that set of three vectors, you get the identity matrix, meaning all three of those are pivot columns, thus all three of them are independent. To span 3 dimensions, I only need 3 vectors, and so these 3 vectors will serve as a spanning set. Any linear combination of them will form another point in R3, and there are no points in R3 that cannot be reached with a linear combination of those 3. Hence, they will span all of R3. No fewer vectors, though, will span R3. If I only had 2 independent vectors, I'm going to span a 2-dimensional space or a plane in R3 and not all of R3. So to span all of R3, I need 3 vectors that are independent. And you don't really need to RREF our standard vectors because they already form the identity matrix. And so you easily can see that those would span all of R3. If I have more than 3 vectors in R3, so if I have 3-dimensional vectors and I have more than 3 of them, they can't be considered a basis because I only need 3 to span a 3-dimensional space. Any set of 4 vectors from R3 are going to be linearly dependent. If I RREF this set, notice I don't get 4 pivot columns, I only get 3 pivot columns, and the fourth column is linearly dependent on the others. I can form that fourth vector by a linear combination of the first 3, which are independent. So these 4 vectors span all of our 3, so they do span the space, but they're not a minimally spanning set because I only need 3 vectors to span R3. I have more vectors than needed. So it is not a basis. A basis is the smallest set you need to actually span your space. Now keep in mind that just because you have 3 or more vectors in R3, it does not mean I have a basis or span the space. Here I have 4 vectors, so on the surface it looks like, well, it's not a basis because I have too many vectors. I only need 3. But in fact, it's not a basis because it doesn't span all of our 3. Only 2 of those 4 vectors are linearly independent. The first 2 are independent of each other. The second 2 are linear combinations of the first 2. So these 4 vectors do not form a basis because only 2 are independent, and thus they span a 2-dimensional plane in R3, not all of R3. If I wanted to talk only about the plane that those 2 span, I could say that the first 2 columns form a minimally spanning space for that plane, but this set certainly does not span all of R3, thus it's not a basis for R3. So to form a basis for a 4-dimensional space, I need 4 independent vectors. To form a basis for a 2-dimensional space, I need 2 independent vectors. To form a basis for a 5-dimensional space, I need 5 independent vectors. And the standard unit vectors will always work as a set to span your space, but any 4 independent vectors in R4 will work to span all of R4. You will be able to create any point in 4-dimensional space using any 4 independent vectors in R4. The standard unit vectors in R2, I and J, 1, 0, 0, 1, will work as a basis for R2. But again, to span a 2-dimensional space, you just need 2 independent vectors. Same thing with R5. I need 5 independent vectors. The standard unit vectors work, but any 5 vectors that are in R5 will create any other point in R5 as long as the vectors are independent. In our previous video about vector spaces, we made up an example in which we pretended we lived in a world that only contained integers, and we defined our objects to be a mod 5, meaning the remainder when you divide a by 5. In that vector space, you would only get as an output 0, 1, 2, 3, or 4. Those are the only possible remainders when you divide by 5. So it's a 1-dimensional space actually, and you could kind of plot it and all the points kind of all fall on the x-axis, and you could just use the number 1 as a basis, because I could multiply 1 by any scalar, any integer, and it would create a number, either maybe 2, 3, 4, or if it was another integer besides 2, 3, or 4, you could then equate it to a mod 5 and divide it by 5 and get your remainder. So the number 1 would actually allow you to arrive at any other object in this vector space by addition or scalar multiplication. 1 plus 1 is 2. 2 plus 1 is 3. So, when you add, you get another integer, and you could define that integer as an object in this space. So again, it's a one-dimensional space, and it can be defined just by the number 1. Sets of polynomials of a certain degree form vector spaces as long as the coefficients are not fixed. If any of the coefficients are fixed, then when you add two of the polynomials together, those coefficients are going to add, and they're not going to end up being the fixed coefficient. For example, if you had all polynomials of the form 5x squared plus bx plus c, when you added any two of them together, you would then have 10x squared and not of the form 5x squared. So that's an illustration of why none of the coefficients can be fixed. So if we considered the set of all polynomials that have an x to the 4th power in them, so ax to the 4th, but these polynomials are not going to have a cube or a square. They will have a linear term, and then they'll have a constant. So we're considering sets of polynomials of the form a times x to the 4th plus b times x plus c. That's the set we're defining. A basis for that set would be the simple polynomial x to the 4th as one element. A second element in the basis would just be x, and a third element in the basis would be 1. So I just need 3 objects in my basis to span and create all polynomials of that form. And by the way, those 3 objects can be equated with the standard unit vectors 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 1. Now, why those 3? Well, in the set of all 4th degree polynomials, x to the 4th can be considered the first position. X to the 3rd would be the second position. I don't have those, hence I will have 0 in that position for my 3 basis vectors. I don't have an x squared, so that position would be 0 for all 3 basis vectors. I do have an x to the 1st power, so one of the basis vectors need to have a 1 in that position, and then I also have the constant. So the last position can be equated with the constant. So again, when you hear people talk about a basis for a set like this, they might actually list the polynomial forms, or they might equate them to the standard unit vectors. Let's look at this set of vectors in R4. I have 5 vectors in R4. So from our discussion earlier, obviously this set is not going to form a basis for R4 because I only need 4 vectors to form a basis for R4. But we also saw an example where we had 4 vectors in R3 and there weren't enough of them to even span R3. So let's RREF this set, and when we do, we obtain the following row-reduced echelon form. The first column is a pivot column. The second column is representing a free variable. The third column is representing a free variable. The fourth column is a pivot column, and the fifth column is a pivot column. So I have 3 pivot columns indicating 3 independent vectors. The first vector is independent of the 4th vector, is independent of the 5th vector. So the 1st, 4th, and 5th vectors are independent of each other. The 2nd and 3rd are linear combinations of those 3. So this set of 5 vectors in R4 span a 3-dimensional space in R4. A basis for the space they span are the vectors that are in the positions of the pivot columns. So the first column, the 4th column, and the 5th column. So 2, 4, 6, 8, 1, 5, 2, 3, 0, 2, 9, 15 form a basis for the space spanned in R4. Now, when I state the basis in this case, I can't just state 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. I can't do that because the vectors with the 1 and the zeros will span a three-dimensional space in R4, but it might not be the specific space that hold those original three vectors. Consider a plane in R3, and there are infinitely many different planes in R3, and so points might be on one plane and not on another plane. So there are points specifically in the space spanned by these three vectors, and there are points in R4 that are not in that space. So to make sure that you're talking about the specific space spanned by this set of 5 vectors, you need to specifically state the vectors that are independent of each other in the original set of vectors. The RREF just showed us which ones were independent. The first, the fourth, and the fifth vectors were independent. The second and third were linear combinations of those three. So again, the basis for the space spanned by these three vectors are specifically 2, 4, 6, 8, 1, 5, 2, 3, and 0, 2, 9, 15. Now the reason why we can use the standard unit vectors or any vectors in R3 to span all of R3 is because if you're spanning all of three-dimensional space, then every point is reached by any set of independent vectors. But in this case, we're not spanning all of four-dimensional space. Instead, we're spanning a specific part or a specific subset of the four-dimensional space. And so we need vectors that specifically keep us in the neighborhood that's actually spanned by these vectors. Again, think about planes in R3. There are many different planes in R3. Some points are on the plane, some points are not. So you can't have R2, which is, the XY plane, you can't have that represent every plane in R3 because it's not the same as every plane in R3. But again, if you were spanning all of R3, then any set of three vectors that are independent will span R3. So if we were spanning all of R4, any set of 4 independent vectors on R4 will span all of R4. But we're trying to span a specific subset space of R4, thus we need these 3 specific vectors or any vectors that are literally just multiples of these 3. Looking at another example, what if we considered the line y equals 4x and all the points that are on that line? State a basis for that space. Well, it's a one-dimensional space, so I only need one vector to serve as a basis. So 1, 4 can serve as a basis. It's a simple vector that is on that line, and it can be used as a basis. So any multiple of 1, 4 will remain on the line, and if I add any 2 vectors on the line, it also remains on the line. So just using simply 1, 4, like 1, 4 does satisfy the rule that y equals 4x, but any multiple of that or any sum of 2 vectors that are on this line will create another vector or point that is on the line. So we can see here, here's the line y equals 4x, and there's our basis point 1, 4. And taking some random scalar 3.17 and multiplying 1, 4 by 3.17, I get a point that is also on the line. If I add 1, 4 and that point, I get another point that's on the line. So you can see that just using simply the vector 1, 4, which satisfies the rule y equals 4x, you can use that to get any other point on the line. Thus, it serves as a basis for the line. Reiterating, a basis for a vector space is a minimally spanning set. It is the smallest set needed to span your entire space using addition and scalar multiplication.